for the linear combinations of vectors. Okay, so given a set of vectors a1, a2 up till an, so can we find the scalars c1, c2, and cn, so that this is this is a combination c1 times a1 plus c2 times a2 plus until cn times an if there are n number of vectors. Okay, so where c1, c2, these are all scalars. So now you see, let's consider that a1 is a three-dimensional vector. Okay, so it's also like xyz three components, and a2 is another such vector. So the example of this is let's say 2 and 3 are two scalars, and then we create a linear combination of the vectors a1 and a2. So how the linear combination works? 2a1 plus 3a2. Now you see, we have learned about how the vectors are added component wise, and we have also learned how a scalar is when you multiply a vector with a scalar, what happens. So you just write this column vector and you multiply each element with 2. So 2 times 0 is 0, 2 times minus 3 is minus 6, and 2 times 5 is 10. Similarly, you also multiply the second vector with 3. 3 times 1 is 3, 3 times 4, 3 times 7. And when we add this, exactly like we did in vector addition, we just sum them component wise: 0 plus 3, minus 6 plus 12, and 10 plus 21. If you see, just the x components, y components, and the z components, they are just being multiplied. Just relate with what we did exactly with the vectors in a graphical form. Now you see the total summation is 3, 6, and 31. Okay, so this is a scalar entity. Now this is a linear combination of vectors, and as I said, 2 and 3 are the scalar items. Now you see, this is also called the set of order triplets of real numbers. Okay, so if you remember, this a1 can also be represented like this. Okay, 0, minus 3, and 5, which will show they are ordered items. So if you change the order, the results will be different and it will be wrong. So you have to make sure that they are ordered triples. Okay, triples because there are 3 numbers, and these numbers can be any real number. So this is drawn from a real number space. Okay, so this is also called R3. This is called R3. So, and it's written as a set of real number and a 3 at the top. So if there are 2 items, like it's in a xy plane instead of a xy z space, so what we will do, we'll call it a R2. Okay, R2. So that will be a set of ordered tuples, okay, of real numbers. Now you see how vector equations are written. Vector equations are telling exactly similar way, given a set of vectors a1, a2, and an belonging to the Rn, which is a n-dimensional vector space. Like this are 3-dimensional, that is the n-dimensional. That means there will be an n number of components. Okay, and another vector, let's say b, which is also n-dimensional. So we are trying to find out, is there a combination? No, is b a linear combination of the AIs? Like I find the equation of AIs with some scalars in such a way that the adding up the linear combination becomes equal to the vector b. Is it possible? That's the question. The answer is a yes or no, depending on whether we can find the corresponding scalar items or not. So also the question can be written in this form. You see, does the following vector equation has a solution? It's a very similar, exactly same question. You can ask this way or this way. Is B a linear combination of the AIs, or does the following vector equation has a solution? We wrote it mathematically: C1 times A1 plus C2 times A2 until Cn times An equal to vector B. Okay, so you can see this, that these 2 equations are same, and these 2 questions, and both of their answers are yes or no, whether it is possible or it's not possible. Okay, we'll see now an example of a vector equation. Now we want to give an example of vector equations. Okay, now let's see, we have 2 vectors a1 and a2, and we have written them in the column vector format. So and b is another vector. So we are trying to find out that is there a solution possible for this equation c1 times a1 plus c2 times a2 equal to b. That means can we find the scalar c1 and c2 in such a way that this equation have a solution? So see this one thing, that here A1 and A2's value we know, B's value also we know. So the variables or the unknowns are basically C1 and C2, okay? So I have written them in a little bit different format, where C1 I have written at X and C2 I have written as Y. So now the linear combination looks like X times the column vector A1 and Y times the column vector A2 equal to the the column vector B. So now we have already seen how we multiply vectors with scalar quantity and do them addition. So these are the standard matrix operation. We are exactly same as vector operations. So you see x times 1 plus y times 2, x times minus 2 plus y times 5, and x times minus 5 plus y times 6 equal to these things. Okay, so now you see so here if we want to find the solution for this, we have to equate the first one, which is x1 or x plus 2y equal to 7, and in that way, so now it's a row wise. Okay, you see I have written this as this. These are nothing but a system of three linear equations. So you see it's a system of linear equation. So they are exactly similar or almost exactly similar. Here the only difference is that there is another unknown, which is z, and here we have just two unknowns, x and y. So you see when we try to solve this, we have to try to find the corresponding coefficient matrix and the augmented matrix. So this is nothing but see this the first two columns are nothing but the vectors x and y associated with x and y. So that is A1 and A2. So this is A1 and this is A2, and the third column is nothing but the vector B. You see how clearly this is related to this set of, so this one and this one. This is the coefficient matrix. A1, A2 are the vectors, and here these are written like that, column vectors, and this is the coefficient matrix, which is B1. So with this video, I tried to relate how from vector we come to the system of linear equations. Okay.